All right, good morning. How are you guys doing? All right. So, been mentioning this every time for the past few times, but on Thursday I will not be able to be here to teach. I'm virtually traveling for a panel session, so I'll be stuck in my office in a meeting all day Thursday and Friday. So, normal office hours will be canceled, and class will be canceled for Thursday. What I'm going to do is we'll wrap up talking about alkalinity and softening today. We left off about here. I think, hang on. Oh, a little forward. We covered a fair bit of this and left off here. So we'll wrap this up, and then I'll talk to you a bit about what I was planning to do on Thursday, just a bit more brief, kind of going over some UV disinfection topics from a little bit more of a research standpoint, some of the recent stuff we've been working on in my research group. Okay, so last time we talked about this 5-step plan to, improve your life or whatever, but to soften your water. And that really was dealing with some aspects of the alkalinity here, in that we can see the same species that are involved when we calculate alkalinity, the CaCO3 as a target to precipitate that, the calcium, the bicarbonate, all of these components that we've been talking about are kind of at play here. And so when we take a look at this particular chart, what we see is if we look at our total hardness, that's going to be all of the calcium and magnesium essentially. Technically, we could add in some other things, but realistically speaking, most other multivalent cations in typical drinking water are going to be quite small. I'm going to, let's see, can you see this? I can't see my marker on my thing, so I'm going to restart this real quick. See if I can fix that. That's bothersome. All right. Well, I'll do my best today, but I'm not able to even see my cursor on the screen that I'm normally trying to use here. So apologize for that. Or I guess I could do this. All right. So for those of you viewing online, it's going to be a little trippy. All right. Apologies, this will just take a moment. All right, and if you are online, I'm not going to be able to see your comments because I'm going to be here. Okay. Hopefully now, yes, now I can see myself. All right. So, sorry about that. If we take a look here, I was talking about the total hardness. Sure, if we add in some other mineral, we could see that right in that spot. That really effectively is not too big of a deal. So we kind of say our hardness effectively is going to be the calcium and magnesium. And so when we take a look then at total hardness, we can categorize it by how it matches up with our carbonate in the system. This is particularly true or with regards to carbonate at kind of near neutral pHs, so bicarbonate primarily is what we look at. So that's why we have bicarbonate here as our measure of the carbonate-related hardness. Now, this is showing up because if we kind of take a look back at our stepwise process, we move any excess CO2 that we can just flush out of the system by reacting it with lime. Then from there on, we can make use of whatever bicarbonate is remaining in the system by reaction with first calcium. This is going to be the first reaction that's likely that we can drive to the right, again by adding the lime. And then if we had a situation where this bicarbonate went out to here, we noticed that we could exhaust the calcium. Maybe we just have very little calcium, maybe we have a lot of bicarbonate. Either way, we could have a bunch of bicarbonate outpacing the calcium, and then we would have some magnesium carbonate hardness. So in this case, we could write that as magnesium carbonate hardness, I guess, right? Or magnesium CH, right? So it would just be like that, the calcium carbonate hardness. And then, of course, we would still have some magnesium non-carbonate hardness. But all of that is really dependent on, how much did we remove given the stepwise process. So in this particular example, we don't have any. If we did have some, we would see it show up, or we would see it removed right here, magnesium carbonate hardness. So once we've removed all the calcium that we can, given the existing bicarbonate, then we could go on to remove magnesium from that. Now, if that was the case, we would not have any calcium non-carbonate hardness, and so this step would essentially not even be there because there wouldn't be enough calcium to do anything with. So as soon as we're starting to add this this soda ash here, then we would be ready for this reaction, but we need to add, again, more lime. So it's all kind of a cascading type of a situation in order to remove one, then the next, then the next. So I'll just say this is a possibility. Okay, does that make sense? All right. Okay, so let's take a look and examine this a little bit closer. So if we have a utility treating 12 mgd of water provided in this example here, and we want to treat it to its maximum softness before distribution, the questions are A, how much lime and soda ash in milligrams per liter calcium carbonate must the utility add? And B, what mass of softening sludge will the plant generate daily? Now I think, yeah, I've got the solution so we can walk through it together. But I'd like to give us a couple minutes to think about what this is going to look like, how we can approach the solution to it. It's probably been a year since I've given it any thought, so I'll be thinking it slightly fresh with you here too. So I'll give you a few minutes. I'll work up some ideas myself, and then we can walk through the solutions, see what we missed. So I think the first thing we ought to be looking at with this problem is our data is given in milligrams per liter. And we're asked to give an answer in milligrams per liter as CaCO3. So one of the first things we ought to do is convert each of these to milligrams per liter as CaCO3. That'll allow us to effectively work on in a way that accounts for the molar differences, right? So we can still be using this mass concentration, but it's as normalized to CaCO3, so that kind of changes all that for us. So I'm not going to do this in the moment, but I suspect that that's something we'll see in the book, in the solutions. And then I went ahead and wrote up that 5-step process kind of to remind us, and we'll probably, would have to flip back through it to check on that to see what all is going on there. But the first one is to remove dissolved CO2. This would also probably, we would probably call that H2CO3. At pH 7.5, we probably don't have much, and it didn't list any, so we can probably assume that's going to be 0. So we kind of don't need to worry about that in terms of what's added. So then we would need to get a measure of the calcium carbonate hardness. And if we think back on it, I think that the equation said we're going to add lime in order to remove this part. So I'm going to go back and check on that. Here we have calcium carbonate hardness. If we add the lime, then we're going to remove some amount of this bicarbonate. So what we would do is determine, probably the best idea would be to set up a plot like this and start walking through, all right, how much carbonate do I have? And in here, they don't actually, let's see, do they specify? Well, this is actually example 6.6, so that works out for us pretty well. I'm going to erase this stuff. So if we look at this plot, this is actually showing us the water from that example. So we can take a look and say, well, the bicarbonate is 135. So we, well, maybe they must have adjusted for, maybe? Okay, I'm a little uncertain. We'll look through the discussions in a moment. But let's say this is the bicarbonate. If we had 200 milligrams per liter of calcium, and we can check, what did they have? Okay, maybe they already converted to as CaCO3. Once we convert to the same values, then we can make this comparison and say, okay, well, we have this much calcium carbonate hardness, and therefore we're going to add an equivalent amount of lime to accomplish that according to this equation, right? So this number 2, we have 1 calcium to 1 lime reacting, and that will yield us this result. So we go back here, and one thing you'll notice is calcium is 2+ and HCO3 is 1-, and we're actually charge neutral in the sense that we're using 2 bicarbonates per calcium. Is kind of how that's effectively working and matching here. Okay, so that would be some amount of lime for this guy. Now, if we have any magnesium in excess of that, we would have number 3. If we plotted it up and it looked like this, then we don't have any excess carbonate past. This does not go past, so we're not going to worry about that step 3. If we did, we could calculate that. And if we did, that would cost us both lime, or just some more lime. Okay, but then we move on to number 4. So we need to account for the remainder, the calcium non-carbonate hardness here. And so in order to do that, we would just get this difference that we know here to here. And in order to get rid of that component, we're going to be adding the soda ash. So we would have 0 here, according to that, you know, if we're following that previous one. And this guy would have sodium bicarbonate. And then last, we would have the magnesium non-carbonate hardness. Basically, would be probably the remaining magnesium there. And this is going to be lime and our soda ash. And if we are doing all of these in equivalence units, then we should recognize that we can kind of just add it up. Like add up the components for this piece, add up the amount for this piece, add up each of these to get a total. Okay, here's the total milligrams per liter of lime and soda ash. We could even add them together because this was asking for both. And that could get us to our answer. And then in part B, so that's the big part of it. And then part B, we have 12 mgd. We'd probably convert this to, I don't know, cubic meters per second or something, or let's say per day. And then we could calculate how many kilograms per day. So we take the flow times the concentration equals the mass. And if we had that flow on a per day basis, we get our answer, right? So I think that should be the process. Does that make sense? Kind of see how that, were you thinking in that manner? Not quite? What were you thinking at? You have any clue where to start on this? Okay, yeah, once you see it here, and I guess maybe some practice setting up a plot like this would be a good help. This tends to help me orient myself with this type of problem. Be like, okay, well, what's happening here, and you know, how do we get anywhere from here?
So will we be given the plot, or should anticipate making that for these type of questions?
Good question. I think I'll probably, and I might have to go back and look at what I gave for you on the homework. I can't remember if I do have you making one of these plots or not. It would be a good idea to be familiar with these plots. So you may need to make one. This would actually be a good example of the type of skill that I want you to have here, is to be able to put everything in calcium carbonate hardness, or you know, as CaCO3, and then recognize what this kind of looks like. Notice here that really this is kind of like two plots. If you just look down here, all we've done is plotted the over here the cations on a bar graph, and then the anions involved, which is in this case just the bicarbonate. And then everything up above that is just kind of labeling what component is this, right? So you could even kind of just make a graph that looks like this, and you just add in a lot more labeling in here, right? You maybe make a dashed line and cut off and all that. There's probably lots of ways you can describe this. The point being, if we're looking at the total hardness, we can categorize it based on what chemical reactions need to happen. So I think I would probably give you this set of reactions if I were to have you do like a big problem with this on an exam. Yeah, but I do think that this would be good for you to recognize and be able to essentially make this plot that is two bar charts, or a bar chart with two plots essentially, and then recognize, okay, this is a cutoff, essentially with the bicarbonate. Okay.
How would you read that?
Yeah. Okay, so what we're looking at is the x-axis is concentration. That's a good question we should have started with. Sorry. So this is the amount of the concentration of hardness, essentially, or of something that relates to hardness. This is very likely as CaCO3. You could write a plot with milliequivalents per liter, and it should do the same thing. And once you have it in either category, then what we're really looking at is, like, and let's just focus here for a moment, like just below that. We just plotted, okay, we have this much calcium. And, you know, a lot of times we might do that as a vertical, right? It's like this concentration at this particular point, like a, you know, vertical bar chart. And then the only other thing is we say, okay, well, if we're going to order this in terms of what is removed from our reactions first, we're going to start from the left to the right. So we, in addition to the concentration as the x-axis, we are also, in some sense, it's almost like a timeline or order of reactions. Also in that direction. So the stuff that's removed first, the first type of reactions that can occur to drive us towards precipitating out calcium and magnesium of some form or another, is reactions with bicarbonate. So that's why we're putting it over there instead of, you know, I don't know, making something that looked like that or something. So to read it, what we ought to recognize is calcium is the first one to be removed with bicarbonate. So those go on the left. And then depending on how far the bicarbonate extends, that's going to tell us something about what's, you know, where we're at with these reactions. All of the stuff up here is just labeling. Right? This is all just stuff we could have stuck on labels in little spots to help kind of orient us on what is happening here. So the calcium the carbonate hardness, out of the total hardness, the carbonate hardness is any hardness relating to this line, right? So that's why this is blocked there. Anything else is going to be non-carbonate hardness. That's just a definition. And then we could step it down and say, okay, well, how much calcium carbonate hardness? This is our reaction number 2. How much of that do we have? How about calcium non-carbonate hardness? This is going to be our reaction number 3, I think. No, I'm sorry, that's number 4. And it turns out we don't have any. So we don't have anything in that reaction. And then, okay, what about if we had any portion let's say if bicarbonate went to here, then this stuff would be our number 3 as magnesium carbonate related hardness. And so we would have a segment here that we could write like that. But that doesn't exist in this example, so I'm not going to finish that out. So that leaves us with number 5 here, magnesium non-carbonate hardness. Okay, is that a little more clear now? Hopefully. All right, great. Okay, so let's, with that, let's take a look at the solution here. Okay, and this part A does exactly what I assumed to be negligible, so that probably explains some differences we saw. So I suppose I was wrong there. Okay, so we say to solve this problem, the first step would be to calculate the amount of CO2 dissolved that must be neutralized. Water's at pH 7.5. We know the bicarbonate concentration at 165. That's what we saw here. Can get that in moles per liter. Then we can take a look at the dissociation constant to find the amount of, that's our H2CO3 or dissolved CO2. And we can get that to be a value here. So we certainly could have started there, and I suppose should have, yeah, and as it converts this to milligrams per liter as CaCO3, we notice, okay, 19.14. That is a fair amount, so I was wrong to neglect that. That was a poor assumption. So we'll go ahead and correct this. Something like 19 milligrams per liter as CaCO3. So let's go back and check what category of stuff do we need to add to neutralize that. It's probably lime, would be my assumption. Yeah, so to neutralize that, we're adding lime. And the reason I was thinking lime is that is essentially going to give us OH minus, which should effectively neutralize the H plus that we get from the H2CO3. I mean, that's sort of my my upfront thinking, but in reality, what we're referring to here is actually just precipitating as CaCO3. So looking at it one way or the other, we see 1 CO2, 1 lime gives us 1 CaCO3. Okay, so that would be a portion there, and if we take 165 minus that 19, that's where we get our 135 here that I was questioning earlier. So that was just my bad. Once we do that, I think these other pieces will fall into place, and this graph will make good sense. Okay. So the second step is to draw a bar graph. So there it is, right? So we correct for the CO2, and now that the CO2 is out of the way, because it would look kind of weird and it would kind of mess with us if we had that H2CO3 or dissolved CO2 right here kind of interrupting this. So that's why we're going to go ahead and get rid of it first, and that lets us start anytime we add lime, it's going to remove something essentially, or lime or soda ash. Okay, so that's the figure we've been talking about, and then I think we could do it just to show those two bars if we wanted to. That's what it's talking about, but abbreviated to show the hardness components. You know, we were given actually a lot of pieces here, including sodium and potassium and all of these pieces. So you could plot all of those on a bar chart like that, but what we want to do is just abbreviate it to the stuff involved in the hardness reactions, which is our calcium, magnesium, and bicarbonate. Okay, so then based on those figures, and these actually might have been what we calculated the other day when we calculated a few as CaCO3. Then we can set up a table for the components of the 5. So here's that table. So if we had stopped and paused and calculated everything from that table a minute ago, we could get this. So here would be a good kind of a good place to start, is just this concentration plot. Or even before here, to say, let's say, starting with, okay, how much magnesium do we have? How much calcium? And bicarbonate. If we get all of those as CaCO3, that would be a good starting point. And then from here, as we go to assemble the bar chart, you probably want to step through and say, okay, here's the concentration of one component that we have, the CO2. We already calculated that. Go ahead and write that up. Because this will let us just add things up in total and get our answer, right? To say some things require lime to be added, some things require soda ash. And on the, this is, so one thing this is showing here is these are additions to count up how much stuff we're adding. And this is something that I neglected and missed when we were talking about part B, is the fact that what we're adding is not the same as what we're yielding as sludge, right? So our sludge is going to be the solids formed. And so I see another mistake that I made is to just consider, okay, how much did we add, right? That answered part A, how much stuff do we add concentration-wise, but we actually have to convert it to, well, we're making calcium carbonate sludge and we're making magnesium hydroxide sludge. So we need to calculate according to those in order to get the actual mass of sludge there. All right, so with that, when we calculate these components and essentially get this graph here, we then know how much of each piece we have. We can write that down. So there's 135, there's 200, and then magnesium was, I guess, 123 beyond that. So that's our 135. We have some calcium non-carbonate hardness. So if we take these two together, that would be that 200 mark that we saw. And then the remaining magnesium non-carbonate hardness. Okay, so that gives us a way to put in all these pieces. This table, you don't have to do this table exactly, but this is what they did to put those pieces all in one spot, add them up and say, all right, our totals for the additions are 297 milligrams per liter of lime as CaCO3 and 188 soda ash as CaCO3. And then the yielding, the amount of sludge we yield from that were these two values. And so they basically set up this entire graph with these equations, right? The 5-step program. We see that we did not have any magnesium associated carbonate hardness. So that was all 0, but we did have pieces in everything else. Okay, so that would have been quite the involved problem, right? We could have spent quite some time doing all those calculations, and coming to that solution. Right. Okay, so the rest of the table can then be completed. It already kind of did that. We'll just talk through it real quick. They were filling out the rest of that table by that stoichiometry, looking at equations 1 through 5 to stepwise go through it to say, okay, how much, let's say in step 2, we're adding lime and we're ending up yielding 2, for every 1 molecule of lime, we're yielding 2 molecules of CaCO3, or whatever the situation is. Okay, so then we can stoichiometrically equate them. Looking at calcium carbonate solid. Okay, so it just walks us through each of those components. Yeah. Okay, so that's just stepping through each of the equations written out or spoken out here as what was happening. Okay, so that's just them walking through the 5 equations saying, okay, we started here, we made this much precipitate. Went here, this much precipitate. Here, we didn't have this reaction. Here, we had more calcium carbonate. And then the final step was we had calcium carbonate and magnesium hydroxide solids. So overall, we're adding calcium, and sometimes, calcium in the form of lime to remove calcium. And then we are adding some bicarbonate to remove the last bit of calcium and magnesium. All right. So then I think there's one last thought here about how low can we go? Maybe that's just built in. Okay, so part B is, that was all part A. Part B is now talking about the sludge, which I think that table that they built already basically gets there. So in this example, they found 477 milligrams per liter as CaCO3 for the calcium carbonate solids that we produced, and 123 of magnesium hydroxide as CaCO3. So we can add those up, get a number, and then account for our flow rate like we talked about. So had we converted to actual sludge before going to that, then we would have been in good shape. Okay, so then they just do the same thing, right? We put it into days, put it into liters, and then get from milligrams to kilograms. And we get about 25,000 kilograms per day of solids. Okay, and that would be accompanied by quite a bit of water as well. So we try to dewater that. All right, so one obvious thing that we can see from this and that the book is noting is that's quite a lot of sludge handling to soften the water. We are removing the minerals directly, right? But in doing so, it's not just like a nice dry powder. We get these solid precipitates that have some water mixed in them, and it's also the carbonate involved, and not just the mineral itself. Okay, so that's all I've got for softening. Any questions on that? All right. Okay, got rid of it. All right. Oh, my screen went back to doing. All right, one moment. So we've got about 20 minutes or so. So I'm going to give you just a bit of a topical conversation about UV light. Some of the we've already talked about UV disinfection, but some of the research we've been working on the past few years really has to deal with what happens after you disinfect bacteria. Bacteria in particular, some of them have the ability to repair themselves after being exposed to ultraviolet light. So there's a few interesting things that are relevant to when we disinfect our water, especially wastewater, but also potentially drinking water. If you were to use some sort of disinfection and then have your water sitting out, maybe under the light, maybe in the sunlight, that could actually trigger the bacteria to repair themselves, because there's a light-driven activity by some organisms that can repair themselves. So we talked, last time we were talking about UV, we talked about the fact that the solar spectrum has a little bit of UV light. And so there will inevitably be a little bit of DNA damage, especially near the UVB range. And so turns out some organisms, especially single-celled organisms, have some capabilities to repair that so that they could perhaps survive in the environment instead of just dead after one random DNA issue. We have pigment to help counteract that, antioxidants, things like that, and a lot of cells. So it's okay if we lose a skin cell. We're not in trouble, right? That's just going to happen. Bacteria then have an interesting potential to repair. And when we think about, from a research perspective, most of the time practice has used this mercury lamp that's at 254 nanometers, emits that strong emission, and we've learned something about how bacteria can repair from that damage. So we had a question about, well, what happens if we start using these UV LEDs and maybe have a strong peak right around here? Looks like a pretty small shift, but that could have some important implications in terms of what kind of damage is occurring. So we've been exploring that. I showed you this, this demonstration of, okay, how do the dimerizations occur? Where do they occur? What does that mean? Well, there were some researchers in the past 20, 30 years that were really, actually it goes probably even a little past that, but in 2015 they earned a Nobel Prize. And the reason was because they were really aiming to harness this molecule that could do that photo repair. What they wanted to do, well, they noticed some of the bacteria were able to repair themselves if, let's say, you do a disinfection experiment and then you leave it out on the lab, in the lab in the open light, they would actually have less disinfection, seemingly. They're showing this right here. So the light caused them to have, when they left them out in the light, there was less disinfection than when they kept them in the dark. So this spurred them on to say, hey, there's some sort of photo-driven repair mechanism here where it turns out blue or UVA light can drive a process for the bacteria to repair themselves. So what they set out to do was to try to capture this molecule, whatever it was happening. And it turns out there was this enzyme called photolase. Photolase something, I don't know how you'd pronounce it. So this enzyme in these cells was sort of a catalytic or photocatalytic action to repair the cells. And they were thinking to themselves, well, hey, if we could make a bunch of bacteria all producing this and then harvest that, we could put it in sunscreen and people would have much better outcomes and we could maybe cure a sunburn even after that's already happened, instead of just trying to prevent it, right? So it'd be pretty neat if you could actually make use of that. There'd be a lot of medical applications. And what's really neat is they found that literally what was happening is when you had this dimerization that was, like superglue in the zipper, this photolase, if UV takes the two thymines and causes that dimerization, well, UV would go along, the photolase would go along and undo that. And it was actually a light-driven process. So this blue light plus the photolase enzyme caused that repair. Now, it turns out that while it was a great goal to harvest a bunch of this, kind of like penicillin or something, it turns out there's really only a few, like 3 to 4, maybe 5 photolase enzymes in a given E. coli cell or a typical cell. So they had a really hard time even identifying what it was for a long time because there's just so few of them, but they were zipping around the cell repairing pretty quick. This is a little bit better picture of what's happening here. And so this little guy would just run around and grab a hold of the DNA and check it for the damage and repair it. And it's driven kind of like a little photon engine, right? It would receive sort of blue light or UVA light, could activate it, which actually makes a lot of sense. If you have some organism out in the open and it's going to receive damage by sunlight, well, if some light activated system is there, it's only going to run when there's light. When it could be damaged, there's light, right? So it's kind of built, almost designed that way. Okay, so we could take a look at kind of how all that works. This is their work. There's actually a pretty good lecture summary here. So definitely take a look if you're interested. It's not entirely in the weeds with scientific detail, right? It's somewhat approachable. So I would say definitely take a look there if you're interested. It's pretty neat. And so, yeah, as we were setting out to measure, to check what happens with disinfection with LEDs, already mentioned, but that was kind of one of the interesting pieces here is how does this change, or does it affect the amount of photo repair and what happens after the cell has been damaged. So given that we might be changing our industry standard, shifting the wavelength, is that going to change what we already know about the photo repair kind of stuff? And so we did a study looking at 2 different disinfection sources and the outcomes from there. So a bit of disinfection data. We had the red was our conventional mercury lamp, and green was our new 278 lamp. And we see some difference here just in their disinfection. This is just disinfection alone plus some organic matter, not really playing a big part. So nothing too super interesting. One thing we'll see is that we didn't quite normalize by fluence, by germicidal fluence. This would be sort of a total fluence. If we measured by germicidal fluence in terms of how much of this light was actually in the germicidal range, these should pretty well overlap is the idea. And this is one way we could take a look to say, okay, well, how much light does it take to get 2 log reduction? This fluence would be essentially time multiplied by intensity. So we talked about that in the lectures on disinfection. So we could look at what value do we need to achieve, let's say 99.99%. We could identify, okay, that's something like 28 millijoules per centimeter squared, right? And we could get that with high intensity, short time, or low intensity, long time. Wouldn't really matter. So that's bringing back that CT concept there. So what happens after that? If we let the bacteria repair themselves after that disinfection and we put them in the dark, there's a bit of repair that can happen, especially if we give them some nutrition. So this is looking at a couple different scenarios. And we see some of them actually recover pretty well, up to maybe 1.5 logs repair or so. And this is over the course of a 9-hour period. But generally, most of them are maybe 1 log recovery after somewhere around 3 to 9 hours. And we're going to contrast that. That's sort of the baseline, with none of that photolier stuff happening, at least not during this recovery phase. And then we're going to give them some sort of light that's UVA to blue range, so 400 being our visible cutoff. So this would be kind of violet blue, this UVA. And we decided to give them a few different types, something that's more UVA, so a little bit harsher right here. Compare that to something that's really kind of right on the verge, and then some white light that covers a lot of stuff. So we're really interested in, okay, what's it look like? How would that compare if it's sunlight, if it's like evening time, if it's morning? Like, what are the parameters here that might affect it, and does that pre-dosing make an impact? Okay, so here's a bunch of data. This line at the bottom is what would happen if we did not do any disinfection, but we just exposed them to this UVA light. UVA slowly hurts the bacteria, so maybe we'll get 90% removal after 9 hours under UVA light. That's kind of what we're saying. So that's if you were just doing solar disinfection, that's the sort of thing you might find. So these were not damaged up front. Everything else, they actually started up here. We killed them all the way down to here, and then we're checking what happens. Oh, in fact, they probably started up here. We killed a lot of them. Sorry, technically, it would have been 0, yeah. So we killed a bunch of them and let them see how much they could repair from that. So that's what's happening in these graphs for each of these that are increasing afterwards. And so what we see is if a lot of these light conditions, they're repairing quite well and rapidly over the course of 3 hours. Now, if they receive continued exposure to this UV light, they're dying off again. So it's like some of that damage was still kind of present, or maybe they're sort of worn out from repairing themselves, because then they became more vulnerable to this UV light. And we can see that in some cases, the solid lines here are the mercury lamps. So all of these with the solid lines, that's the old school mercury, and the dashed would be the LEDs. So we see perhaps the old school mercury ones in some cases may have better outcomes. Not super clear. This one at least looks like the worst outcome in terms of the net impact. So this was not super conclusive. These were checking kind of different access to nutrients. We also checked, well, what happens if we change the type of light? We can see that some of these looked a lot different, and if we put it on a fluence base, there was something happening here where we were using up all of their photolier's action pretty quickly, or if we gave them more light, it seems like it would happen more or less light. So there's some impacts there. I'm gonna breeze by this a little bit. Ultimately, we didn't come away with super strong conclusions about any one particular spot on this at this point, but it was kind of interesting to see there may be some differences coming out, especially here with this is comparing the 395 to the 365. So harsh light. This black here is the harsh one. And it looks like in general, that so there would be that this one and this one. So the stuff dosed with the LED was a little less susceptible than the stuff dosed with the mercury under the harsh conditions. That changes a bit if we're not looking at quite so harsh conditions. So might be something to account for as we apply the LEDs instead of the mercury lamps going forward. But I think there's a little more that we need to study there. So one of the things we tried to do was model this based on other people's models. They had said, okay, well, if we have this much light, if we have this much dosing, how can we model that? That's something that we've been following up with. The model in the literature doesn't really match our data particularly well, and there were some issues trying to convert that. So that's some stuff we've been working on since then. Okay, so that's just a quick little rough sketch of some stuff we've been working on. Been doing a little past then. If you guys are interested in taking a look at another aspect of this UV LED stuff, we have some stuff going on using them for advanced oxidation processes, and my graduate student will be giving a guest lecture in the other course. He has a course during this time. So at noon, in like 3 doors down, on Thursday. If you're curious, you can go there. I also have, on my YouTube channel, essentially this lecture, but for the advanced oxidation stuff posted. So if you're curious about that, please let me know, and I can point you to the right place. But I think that's about all I have for you today. So no class on Thursday. I'll probably post some materials about the Flint water crisis and encourage you to spend that class period reading or taking a look at some of that material. Next week we'll have kind of exam review and the exam, I think is the plan, right?